There are different ways to do data standardization, and in this video, I'll go through several common methods. We will see that the results are the same. And since we already understand the concept of z-score, now it's time to apply it to our data. So let's go to the data and choose the cholesterol column. The first value in the column is xi. What I do is subtract the mean of the column from each value and then divide the result by the standard deviation, which is called sigma. After that, I apply the abs method to take the absolute value. So now we only care about how far a point is from the mean, regardless of direction. This will give us the z-score for each data point. So this is how we manually standardize the cholesterol column, and this same logic can be applied to other features too. Now we can use this formula and say any data points that goes beyond mean plus minus 3 standard deviation is considered an outlier. If our data is normally distributed, we can also say what percentage this means. Any value outside mu plus minus 3 sigma lies beyond 99.73% of the distribution. But if the data isn't normal, we cannot assign a precise percentage like that. Let's test this and print the shape of the original data frame and the filtered one. So this prints 597 vs 567. That means 30 rows were removed, but it's very important to understand those 30 values are not all outliers. Some are just missing values. Let's check how many nulls we actually have in the cholesterol column. As you can see, it's 23 missing value. It means that out of the 30 rows earlier, 23 of them are missing value, and only 7 are true outliers. This distinction is very important. Missing values are not outliers. Now we want to tell Python not to consider the missing values when we calculate z-scores. So how can we do this? Just like before, I filter using z-score condition, but now we also drop missing values using. So here I use drop NA. Here access is equal to 0, means we are dropping rows that have missing values. Then we compare the shapes. So it prints 574 vs 567. That means the difference is 7, confirming again that 7 rows are true outliers and the rest were just nulls. Another way to calculate outliers with z-score is by using upper and lower bounds. Then we filter the data frame to keep only values greater than upper or lower than L or lower. This gives us the same 7 outlier rows as before. Let's try another approach using NumPy. I define an empty list out to store outliers. Then I write a function. As you can see in the code, inside the function, I calculate the mean and put it in M. Then I calculate the standard deviation and store it in SC. Then for each value I in the column, um, it calculates its z-score. If the absolute z-score is greater than 3, it added to the out list. This method gives us the same 7 outlier again. Now let's use a scikit-learn standard scaler. We import from the preprocessing module. We follow three steps: initialize, fit, and transform. This standardizes all columns, and the result is shown as a NumPy array. To bring this back into a data frame format, we wrap it with a data frame, then do the three steps: initialize, fit, and transform. So then we include the original column names and index. Now we have the scale data in data frame form, and we can choose any column to extract outliers. In the next steps, we can compare this z-score method with IQR to see the differences. But remember, even z-score is powerful method. It has also a downsides. The mean is sensitive to outliers in z-score. A better option in some cases might be to use robust z-score, which is more resistant to extreme values. Also, there is other methods which called model-based methods. These are more advanced and powerful, especially when dealing with multidimensional data. These algorithms like clustering, local outlier factors, isolation forests, and so on. These approaches evaluate patterns across multiple features and can detect both outliers and noise in a more holistic way. Thanks for watching.